Hello everyone, my name is Rooji and I'm a student at Indian Institute of Science. Today I'm here to talk about the usage of replication coded storage to achieve low latency in a distributed storage system when the servers are memory constrained. This is a joint work with Ajay Badita, Pradeep Sarvepalli and Parimal Parag. We know that in distributed storage systems, we have data stored on multiple servers in a distributed manner. And one approach to minimize the file access delay in such systems is to introduce redundancy in the data storage through coding and allowing this data to be accessed parallelly. Two most popular approaches towards this coding are replication coding and maximum distance separable or MDS coding. Here we see a replication coded storage where two files are replicated twice and stored. And here we have the same two files which is encoded via MDS coding. And when we are doing the MDS codes, we see that in order to recover the two files A and B, we only need to download any two encoded simples. And we consider a setting where each server has a memory constraint and can store only a fraction of the file. Then we fragment the file into, say, V fragments, and we encode them at a replication, we replicate them at a replication factor R, and we have VR encoded fragments. Here we have an example where a file A is divided into two fragments and replicated twice. Then we also show a finer fragmentation of the file and its replication coding. Now these encoded fragments will be placed over a system of B servers, each having the capacity to store alpha fraction of the file, or it can store alpha V fragments in total. So let's consider the previous examples where a file was divided into 2 and 4 fragments and replicated. In the first case, we have the file divided into two fragments and replicated twice. This is stored on a system of 4 servers, each having the capacity to store half the fraction of the file. And next, the file is divided into 4 fragments and it is stored on the same system after replicating twice. Note that by introducing this finer fragmentation, we are allowing these 4 fragments to be served parallelly by the 4 servers, which is likely to have a positive impact on the download time of the file. And throughout this talk, we shall refer to the placement of these different fragments across the servers as the placement scheme. And we are interested in finding the storage schemes that will offer a good download time performance. Now let us look at the file download. We consider a single request in the system and it will be forked onto all B servers simultaneously, and it will start downloading the file fragments from the servers in succession. A request will leave the system only once it has collected all the fragments which is necessary to decode the file. So here in this example, we have a system of 7 servers storing a file which is divided into 7 fragments and each replicated thrice. Next, say that the fragment 1 is downloaded first. Then we assume that its redundant copies, which is stored on server 6 and 7, will turn useless and will not be downloaded anymore. And now the second fragment will be downloaded parallelly at servers 1 and 2, and all other fragments will be served by 1 servers each. And say that fragment 2 and fragment 3 gets downloaded one after the other. Now we introduce a parameter, the number of useful servers after lth download. This is equal to the number of servers which holds at least one fragment that is not yet downloaded. For example, we see that in these pictures, the number of useful servers remains 7 until the third fragment is getting downloaded, which is when the first server will turn useless, and N3 will be equal to 6. Now, if the fragment download times are IID exponential distributed with rate mu, then the joint rate at which the fragment will be downloaded will be NL times mu, as there are NL servers which is going to serve the request in parallel. Now, the problem that we address is minimization of mean download time. We know that the download time is the sum of download times of the distinct fragments needed to decode the file when the file is replication coded. And fragment download times are dependent on the number of useful servers, particularly higher the number of useful servers, lower will be the average fragment download time. Also, the number of useful servers is going to decrease from the total number of servers B to 0 as the download progresses, as we show in this graph. Then we establish the following bound, and that is the normalized mean download time is lower bounded by 1 divided by mu times the mean number of useful servers, which is averaged over all fragment downloads. Now we reformulate our problem in the following way. That is, instead of minimizing the mean download time, we are interested in minimizing this lower bound, or equivalently, we would like to find a storage scheme that maximizes the mean number of useful servers averaged over all fragment downloads. So before formalizing the problem statement further, let me quickly discuss some prior works. We have listed only very few articles that are related to our work. So firstly, it has been established that MTS codes will outperform replication codes in minimizing file access delay. And some recently introduced coding techniques with really good latency performances are rateless codes and staircase codes. This work on staircase codes that we have cited suggests that the subfragmentation of files and allowing each server to store more than one fragment will help in improving the download time performance. Our model also employs the same technique, where we fragment each file prior to replication coding and storing it on a system of memory constrained servers. However, we assume that all fragments are equal sized, unlike in staircase codes. Now, before going into our model, let us first discuss about the performance of MTS codes in our setting. That is, we have a file which is divided into V fragments, and it is MTS coded into VR encoded fragments and stored on a system of B servers. Here we have a file divided into just two fragments, A1 and A2 being MTS coded and stored on a system of 4 servers. Suppose we download one fragment here. Now all the other 3 remaining fragments, and hence the remaining 3 servers, will remain useful, as MTS codes need only V fragments out of the VR encoded fragments to decode the file. Let us compare this against a replication coded system. So here, when one fragment is downloaded, its redundant replica is also turning useless. So that is, in MTS codes, the reduction in number of useful servers will be the least compared to any other code, not just compared to the replication codes. And hence, it will provide optimal performance in the sense of maximizing the number of useful servers. But then why do we prefer replication codes over MTS codes in this study? Well, here are the drawbacks of MTS codes. First is the decoding complexity. For example, let's say that in order to download the file which is stored here, we download the 2 fragments A1 plus A2 and A1 plus 2 A2. Now this has to undergo a complex decoding process in order to obtain the original file fragments A1 and A2. This decoding might also contribute to the file retrieval latency. And next, if we want to scale up the system by adding new nodes, then rebalancing of data across these nodes is going to be way easier if we are employing replication codes instead of MTS codes. Also, for implementing MTS codes, we need the alphabet size of the underlying field to be large enough, and this puts some constraints on the fragment sizes that we can choose. So here we have our coded storage model. We call it the alpha VR replication coded storage. For example, in the picture, we have a file which is divided into 7 fragments, replicated thrice, and stored over a system of 7 servers, each with a capacity to store 3 out of 7 fragments. So this is a 3 by 7, 7,3 storage. Further, we call the set of fragments which is stored on each server as a fragment set of that server. For example, fragment set of server 1 is the set 1, 2, 3, as server 1 stores the fragments 1, 2, and 3. Now note that this entire storage scheme can be simply expressed in terms of the collection of the fragment sets across all the servers. So now alpha VR replication coded storage over B servers is defined in terms of the sequence of these fragment sets, and we have this collection of fragment sets satisfying the condition that each server will be storing just alpha V fragments, where alpha is equal to the fraction R by V, where R is a replication factor and V is the total number of servers. Then the problem statement is to find the storage scheme within this alpha VR replication storage ensemble that would maximize the mean number of useful servers averaged over all fragment downloads. And now, before attempting to solve this problem, let's think about this question a bit. So for a fixed VR number of encoded fragments and B server system, we can have a very large collection of storage schemes, and we need to find the optimal one in it. Also, the size of this collection will grow exponentially with the number of fragments and the servers. So this is not an easy problem to solve at the outset. And we work towards a solution by first noting a simple upper bound on the number of useful servers. So at the initial stages of the download, which is shown in the first picture, we expect that all servers shall remain useful, but towards the final stages of the download, it will start decreasing. That is, in the second picture, we have only 2 more fragments to be downloaded, and the maximum number of useful servers that we can have here is 2 times the replication factor R. Okay. So this is exactly what we have in this bound written on the left hand side. That is, NL is bounded by the total number of servers B initially, and later it is bounded by V minus L times R, where V minus L is the number of fragments which are not yet downloaded. And upon rearranging this, we get the bound on the right. That is, the normalized average number of useful servers is bounded by 1 minus a term that decreases with the increase in number of useful number of fragments. In fact, as V is asymptotically large, this bound will converge to 1, which is the fundamental upper bound on normalized average number of useful servers. So next we have a trivial case where there is no memory constraint at the servers. That is, we can allow the entire file to be stored on each server. And if we allow this, as demonstrated through these pictures, we see that all servers shall remain useful until the completion of the download process, and this will hit the fundamental upper bound. And we are not interested in this case, and we would like to examine the case where alpha is less than 1, or the servers do not have the capacity to store the entire file. Then we suggest a randomized placement of fragments over the servers. And how do we do this randomized placement? Just pick any of the replicated fragment and then just choose one server among the B servers uniformly at random and place a fragment on that server. And we may continue this process until all the fragments are placed. Now, the issue with this storage is that we cannot implement this placement when the storage capacity of each server is limited. And this is because we have no control here over the number of fragments which will choose each server. So then we should modify the system a little bit so that each server must be offered with a capacity to store the entire VR number of fragments. And we call this a randomized BVR replication coded storage. So we already know that the setting that we are considering is that of a memory constrained server system. So why are we interested in this randomized BVR replication coded storage? We are interested in this system because when we increase the number of fragments, which say the fraction R by B fixed, as we show in this picture, we will see that the normalized number of fragments which is stored at any server converges to the factor R by B. That is, the randomized BVR storage scheme is an alpha VR storage scheme asymptotically in V. And this convergence, we can show it in an almost sure sense. And now we also show that the normalized average number of useful servers of a random BVR replication storage ensemble is given by this expression, which converges to 1 as the number of fragments V is asymptotically large. That is, this randomized storage scheme that we have proposed, it is the optimal storage scheme for any encoding strategy and not just within the class of replication codes. Here we have the plots. So here the solid line will be indicating the normalized average number of useful servers, and the dashed line will be indicating the upper bound on this normalized useful servers. And as we are increasing the value of V, which is the number of fragments, we see that the gap between the actual performance and the upper bound is diminishing. And finally, it will converge to the optimal performance, which is also offered by the MDS codes. Lastly, we check whether the number of useful servers is indeed a good indicator of the download time performance. So we saw that as number of fragments increases with the fraction R by B fixed, the number of useful servers will increase in a randomized BVR storage scheme. And so correspondingly here, we see that there is a decrease in the average download time of the file as well. So this suggests that this metric that we have chosen, which is the number of useful servers, is indeed a good indicator of the download time performance. And let me conclude my talk. So we studied codes for distributed storage system with storage constraints and file subfragmentation for achieving low latency. And when download times are exponential, we reformulated the problem as maximizing the mean number of useful servers instead of minimizing the download time. And in this new setting, we show that MDS codes are optimal. And when there are no memory constraints of the server, even replication coding can achieve this optimal performance by allowing the entire file to be placed on every server. And when servers have memory constraints, which is the interesting regime, we show that replication coding combined with probabilistic placement will be optimal when the number of fragments are asymptotically large. So that is where I would like to stop this talk. So thank you for listening.